as sophomores to make a video for the first section of the thermochemistry notes. So I'm going to call these thermochemistry part 0 because I know I already have thermochemistry parts 1 and 2, and this goes before them. So here we go. These are just some words that you're going to know by the end of this particular video, so I just kind of wanted to give you a heads up about what you're fixing to see. Just a quick clarification on the difference between calorie with a little c and calorie with a big C. The calorie with the little c is the chemist's calorie. It's defined as the amount of heat needed to raise the temperature of 1 gram of water, 1 degree Celsius. So a calorie is based on the specific heat of water. A big C calorie is basically, it's a kilocalorie, but this is the nutritionist's calorie because it's what's used to measure the energy that you get from food. And then this is just a little blurb that I threw in there to show you that fats have twice as many calories as carbs and proteins do, which is what makes them so gosh darn hard to get rid of. So what these notes are all about is the first law of thermodynamics. We get to the second law of thermodynamics when you get to entropy and Gibbs free energy and all that stuff. We're sticking with the first law in this particular one, just sticking with H here. It's also known to you guys as the law of conservation of energy. Basically says energy can't be created or destroyed, but it can be converted from one form to another, say, chemical energy into heat energy, or, later when we talk about electrochemistry, we can take chemical energy and convert it into electrical energy. You can change energy into all different kinds of forms, but ultimately you're going to end up with the same amount that you started with. So just kind of talking about exothermic versus endothermic processes, starting with exothermic, everything that we talk about in terms of energy exchanges and stuff like that is going to be in terms of the system. Not talking about the environment, we're talking about the system. And the system is going to be either the object we're studying or the reaction that we're studying, but not the surrounding environment. And so often, this gets a little confusing because us humans, we are almost always a part of the environment, which is why, since you were 6 years old, you've taught that an exothermic process feels hot. It feels hot to the environment, which is where we are, because the system is transferring heat to the environment, to its surroundings. Basically what happens is the potential energy that's stored in the system, usually in the form of like chemical bonds or something, is converted into the heat energy that gets released. So I don't want you to think, okay, well, if the surroundings heat up, then the system must cool off. Now, the system typically doesn't experience any kind of a temperature change. It's just that, let's say we had some methane gas, CH4. There's 4, I'll draw the Lewis structure for this. There's 4 bonds right here, and when you burn methane gas, you break these bonds, and then you form the bonds of the products. And so the potential energy that's stored in the bonds gets converted into heat energy. And there's a little bit more involved in that, having to deal with the bond energies of the products versus the bond energies of the reactants. But for right now, this is enough. An endothermic process, on the other hand, is where the system sucks in heat from the surroundings, and so to us, a member of the surroundings, it will feel cool. And basically what happens is the heat energy that the system is sucking in converts that heat energy into a potential energy in the system, again, usually in the form of a bond or an interaction, maybe a solution process. It could be any number of things that is used to convert that heat energy into a form of potential energy. But, same thing back here, I didn't want you to think that the system doesn't cool off. In an endothermic process, the system doesn't heat up. It takes that heat energy and converts it into something entirely different. All right, so a couple of things to think about here. Situation number 1, imagine you have an ice cube melting in your hand. Is the melting of ice endothermic or exothermic? And then explain it in terms of the system and the surroundings. So think about this. You have an ice cube melting on your hand. The ice cube in this case is going to be our system. Your hand is the surroundings. So is this melting endo or exo? Well, if you think about it, in order for a solid to turn into a liquid, energy has to be absorbed. And that heat energy that is absorbed, so we have energy coming in, I should have wrote a capital E, sorry, is being used to increase the kinetic energy of the solid to the liquid, giving the particles in this substance the energy to break those intermolecular forces and enable the particles to be able to slide past each other and be a liquid. So, is an ice cube melting endo or exo? Since it requires an input of energy, it is endo. Imagine warming your hands near a campfire. Is the campfire endo or exo? Well, again, think about it. The campfire is our system, and again, your hands are the environment, the surroundings. So the campfire, the burning of wood, the burning of logs, is ultimately an exothermic process because the campfire is releasing energy to the surroundings. Now you might go, okay, well then, if this is an exothermic process, if it releases its energy, why doesn't it just happen? And that's when you have to look at things in terms of basically a reaction progress diagram or graph or something like that, where you have energy on the y-axis and you have time on the x-axis. If you start out with your reactants and then you end with your products at a lower level, so your reactants are up here, your products are down here. This is an exothermic process where the energy of the reactants is higher than the energy of the product. So this energy difference here is what's going to get released to the environment. Problem is, this reaction isn't going to just happen. You have to have what's called an activation energy. So you have to have energy applied to it. So like with this campfire, the energy applied could be a match or a lighter or, rubbing two sticks together, whatever it might be. So this activation energy has to be achieved, and then once it is, then the reaction will proceed in the forward direction and all of this energy will be released. An endothermic graph pretty much looks the opposite of this, where the products are at a higher level than the reactants, and so the difference in energy between the products and the reactants has to be absorbed. So there you go. All right, so that leads us to H, enthalpy. Enthalpy is the property of a system that talks about the flow of heat between a system and its surroundings. Of course, it has to happen at a constant pressure. And I just threw this in here, the fact that H is a state function. Basically what that means is that all that matters is that you got from point A to point B. It doesn't matter if you went straight there or if you went some convoluted way to get to point B. All that matters is you went from here to here. The middle steps, how many reactions you had to go through to get from A to B doesn't matter. Just the middle, or just the beginning and end matters. Now, I told you before in the QMCAT video that you can't directly measure heat. And the reason that you can't directly measure heat is it's just not possible. The only thing that you can measure is a heat transfer. And so delta H is defined as the heat absorbed by the system during any kind of change. And so for an endothermic reaction, since the heat is in fact absorbed, delta H is positive. It's going to be negative for an exo because you have to think of it in terms of the system. What happens in an exothermic reaction to the system? The amount of heat in the system, or the amount of energy in the system, goes down. And so because the amount of energy in the system goes down, the change in enthalpy is negative because it decreased. You're not going to have I think I'm getting to it. I'm getting ahead of myself. Sorry. Okay. Two possible units for delta H are either going to be kilojoules, or if you're dealing with a molar enthalpy, it'll be kilojoules per mole. And delta H is directly proportional to how many reactants or products you have, and that kind of makes sense. If you had a campfire built out of one log, it's going to be a very small fire and give off a little bit of energy, versus if you had, the Great Aggie Bonfire, then you're going to get a ton of energy out of that, and you can stand a football field away from it and still feel the heat coming off that sucker. I kind of don't want to get into a lot of detail about this, except to show you that anytime you see that you have a subscript attached to a measurement, that subscript is just simply meant to be a descriptor on that measurement. So like, the vape refers to the enthalpy change of vaporization. BDE refers to the enthalpy change of bond dissociation energy. Delta HF is the enthalpy change associated with formation of a compound. And so this is kind of like the scientist version of an adjective, really. So, quick practice. How many kilojoules of heat are absorbed when 25 grams of methane burn in air? And then I'll give you the delta H of combustion, since we are dealing with combustion here, of negative 802 kilojoules per mole. Now, a little bit of a typo here. I didn't mean to put the word absorbed. I should have put released. Because we all know that burning methane releases a whole heck of a lot of energy. So, my bad on the typo. Just get over it. I'm not perfect. So this is one of those questions where you're going, okay, where the heck do I start? Well, ultimately, you know that you want to get to kilojoules. And so getting to kilojoules, well, I see kilojoules right here. And anytime you see something per something, you know that that particular number can act as a conversion factor. And so if we were to rewrite this as a conversion factor, it'd be negative 802 kilojoules per mole. And so that could be our conversion factor. Well, I can get to kilojoules using this, but I have to go through the mole. Well, I don't have mole, but I do have mass, and I know what I'm burning. So can I get from mass of something to moles of something? Of course I can, using the molar mass from the periodic table. So that's what I'm going to do. I also have given you guys the tip before of always start with your simplest number that you're given. I'm given two numbers here, one with the units of grams, one with the units of kilojoules per mole. This is my simple number because it only has a single unit as opposed to multiple units. So I'm going to start there with my 25 grams of methane. Methane is CH4. And using the molar mass, I'm going to convert it to moles. So I know that the molar mass of methane, this is 12.01, and each of these is 1.01 times 4, so 16.05 grams of methane per mole of methane. Whoops. And then from here, since I'm in moles now, I know that methane has a heat of combustion of negative 802 kilojoules per mole. So for every mole of methane, probably didn't have to write the CH4 over and over again, but whatever. I'm going to have negative 802 kilojoules. I'm going to have an energy change of negative 802 kilojoules, or I'm going to release 802 kilojoules. So I'm going to go ahead and keep that negative in there. So from here, I get to cancel out my units. Again, try to work these out without using a calculator. I can kind of see that's 25 and 16. These numbers, okay, 25 is kind of close to 8, and so I know that this is going to be about, what is that, 3 halves, give or take a little bit. So about 3 halves of this is going to be 1,200 and something, and when you plug this into a calculator for an exacting, if this was a AP question, multiple choice question, estimating about 1,200 would get you close enough, and you'd be able to go and pick through your answer choices. But if this was a free response, yeah, I'd go ahead and plug it in, and you would have negative 1,250 kilojoules of heat, or if you wanted to use the words, you would say 1,250 kilojoules of heat was released. All right, reversible reactions. If delta H is positive for the forward reaction, then it would only make sense that if you flip the reaction, then you're going to, instead of maybe absorbing the energy, you're going to release the energy. And because of the law of conservation of energy, it has to be the same amount. So the example I have here, this one is the melting of ice, and this is the freezing of ice. So it would make sense that the energy that has to be absorbed to melt the ice is equal to the amount of energy that's released when the ice refreezes. Couple of things to keep in mind. That positive or negative on the delta H is not a positive or negative value of energy, because of course you can't have a negative amount of energy. Now some astrologer people might say, oh, you have a negative energy, but okay, no, scientifically speaking, negative energy is not possible, at least not yet. Maybe one day it could be, I don't know. I've learned to never say never in the science world. But the sign on delta H is only indicating direction flow into or out of the system. And of course, the reasoning for this, the reasoning that the magnitude of the heat change for reverse reaction has to be the same, is because of the law of conservation of energy. You can't create or destroy it, it has to stay constant. This is just a little refresher of how the sign on delta H for your phase changes. Long time ago, way long time ago, we did what you guys probably thought was the most pointless lab, where I had you melt ice. And I had you record the temperature of ice melting into a liquid and then to the boiling point. And you drew a graph that looked a little something like this. You had this, and then it started to melt, and then all the solid was gone, and the temperature started going back up again, and then it started to boil, and it leveled off. And we never got past this point right here, but if we were in a closed container and could keep a hold of all that water vapor, once all the liquid water was gone, and it was just water vapor, the temperature would start going up again. So just to kind of put some labels on here, temperature would be on the y-axis, energy would be on the x-axis. And at this point, we had a solid. Here we had a solid changing into, that's an arrow, I swear, a liquid. Here we just have a liquid. This we have a liquid changing into a gas, and here we have just a gas. And the reason that it flatlined at the phase changes was because the phase change, instead of the energy being applied to just increase the temperature of the system, the energy being applied is now going to, in this case, overcome the intermolecular forces that was holding the particles in the solid, or here, overcoming the intermolecular forces that's holding the liquid together and allowing it to completely escape into the gas phase. So anytime you move from solid to liquid or liquid to gas, that results in an increase of energy in the system. And so going from solid to liquid or from liquid to gas is always going to be a positive delta H, an increase in enthalpy. Flip side of that, if you go from a gas down to a liquid, that requires a release of energy. The kinetic energy decreases and that energy is released to the environment. Same thing with solid down to a liquid. This energy has to be released, and so this is associated with a negative delta H, or a decrease in energy of the system. Kind of covered that just then. And then what would be the sign of delta H for sublimation? Well, sublimation is going from a solid directly to a gas. So you are increasing the energy, so it's going to be positive delta H. Deposition, the opposite, going from a gas directly to a solid, like the freezer burn that gets on everybody's nerves in your freezer. That results in a decrease in enthalpy because you are decreasing the amount of energy in the system. All right, calorimetry. Kind of already talked about this in the Q MCAT video, so just to save time, I'm going to skip right over this. Skip right over that too. Okay, last thing that I wanted to do in this particular video, and then we will call this one a day. Molar heat of combustion of liquid ethanol. What is it? If the combustion of 9.03 grams of ethanol causes calorimeter to increase in temperature by 3.54 Kelvin, and then they give me the heat capacity of the calorimeter. So this is another one of those questions where you're looking at it going, oh my God, where do I start? Well, look at what you're trying to find. What is the molar heat of combustion? Molar heat of combustion is delta H combustion, which has the units of, since it's molar heat of, it's going to have the units of kilojoules per mole. So this is where I want to end up. I want to end up in the units of kilojoules per mole. So let me look at what I have here. I have 9.03 grams. I know that there's a relationship between grams and moles, so I get the very distinctive feeling that a molar mass of ethanol is in my very near future. And then for kilojoules, let's see, I have a temperature, and then I have a value that relates kilojoules and temperature, so I'm pretty sure I can use these two numbers to get to kilojoules. So let's get started on that. First number I came to was a 9.03 grams, so that's where I'll go ahead and start. So I have 9.03 grams of ethanol. And in case you've forgotten, ethanol is C2H5OH. And the molar mass of ethanol, if you added all this up, 24 and 5 plus 16 and 1, gives you 46.08 grams per mole. And so my grams cancel, and I have moles. I have half of my units already. So all I have to do is take this 9.3, divide it by 46.08, and I get 0.196 moles of ethanol. Now the other part of my unit is the kilojoules, so I'm going to use this information right here to find my kilojoules. Starting with my 3.54 Kelvin, and using this as a conversion factor, just to rewrite it, just to show you what it looks like, 75.8 kilojoules per Kelvin, which is actually quite a bit. That's pretty good. And so for every 1 Kelvin, it's going to take 75.8 kilojoules of energy. So take these, multiply it together, 3.54 times 75.8, and you get 268 kilojoules. Now, this isn't my final answer. I need my final answer in the units of kilojoules per mole, so let's put these two numbers together in a way that I get these units. So 268 kilojoules per 1.96 moles. And that's going to be equal to 1,369, or your sig figs, you can just say 1,370 kilojoules. And that's the molar heat of combustion of liquid ethanol. So should this be a positive or negative number? You got to think about it. Is this an endothermic or exothermic process? It's combustion. It's extremely exothermic. So plop a negative out front. And the reason that it is a negative is the calorimeter increases in temperature by 3.54 Kelvin, which means that increase in temperature was caused by this reaction, the combustion of ethanol, releasing its heat, releasing its energy to the calorimeter. And so we're basically saying that, the heat gained by the calorimeter, which is the positive 1,370 kilojoules, is equal to the heat lost by the combustion reaction, which would be same size, opposite sign. And now you can kind of watch along with the other videos. I actually think I start with this question in the part 1 video, but you know what? Repetition is the key to learning, right? All right, guys. Y'all have a great day.